Welcome everybody to this lecture on the anaerobic treatment of domestic sewage, centralized and decentralized applications. To start, we need to understand what are now the principles of anaerobic sewage treatment. What are our objectives? Well, we would like to remove the biodegradable organic compounds by converting them into methane, like in any anaerobic reactor. In addition, we would like to remove settable, non-biodegradable compounds that come along with the primary solids inside the sewage. Then we would like to stabilize the retained sludge, which is the primary sludge, the primary solids, as well as the newly grown bacteria. And in the meantime, we would like to improve the dewatering characteristics of the sludge. If you combine this, and we bring this to an anaerobic reactor, then in fact we can design one single reactor that comprises 5 different units. An upflow anaerobic sludge blanket reactor is currently the most applied anaerobic reactor for municipal sewage treatment. And in fact it comprehends these 5 units compared to the conventional activated sludge process. First, the primary clarifier, the biological reactor, third, a secondary clarifier, 4, a sludge thickener, and 5, a sludge digester. If you then compare that, this is a schematic layout of an activated sludge plant. The raw sewage comes in, you have screens, you have a grit chamber, sand removal, then you have primary sedimentation, you have an activated sludge plant, secondary sedimentation, and you have the tanks for sludge digestion, a thickener, a digester, and a dewatering unit. If you now compare this to an anaerobic setup, in fact we combine these 5 units to a single system. We still have the screens, we still have grit chamber, but we have one single high rate anaerobic reactor, and for sludge treatment we only need the sludge drying beds, since sludge thickening and digestion is already done inside the anaerobic reactor. But what you do see is that we need an additional treatment step after the anaerobic reactor, a so-called polishing step, which can be a pond system, a trickling filter, a wetland, or activated sludge or whatever. Now, what you also see, there are some comments where put at the screens and at the grit chamber. So in an anaerobic reactor it is very important that you have a very good grit removal, sand removal up front. Otherwise the sand will accumulate in the upflow reactor. The grit chamber you can combine with fat grease removal, because accumulation of fat and grease inside the anaerobic reactor may impact negatively the bioconversion. Now then, the screens itself, we have different types of screen. You have coarse screens of 20 mm, but if you have a large sewage treatment plant, it's good to equip it as well with a fine screen of 4 to 6 mm, just to prevent that these small solids will accumulate in the anaerobic high rate reactor. But nonetheless, we can economize on the number of tanks. So in principle, we have already some capex reduction in the capital exploitation cost of a municipal sewage treatment plant. The general layout of a sewage treatment plant is represented here. Again, you have the influent, you have the screening, coarse and fine screening, then you have grit sand removal, then you have your upflow anaerobic sludge blanket reactors. We often make more units in parallel, so if we clean one unit we can put the other hydraulic flow to the other units. Now after the anaerobic reactors, the upflow anaerobic sludge blanket reactors, the water will go to a post-treatment system that may consist of polishing ponds, trickling filters, rotating biological contactors, etc. Now the sludge is already stabilized. What you see is the orange line, it's a sludge line. The sludge is discharged to simple sludge drying beds where you have a cycle of less than 1 week for you have a dry sludge. And this sludge, in principle, if legislation allows, can be used as soil conditioner for or fertilizing agents in sandy soil. Now we produce biogas, and that's which is indicated by the green line. Now, the question we often get, yeah, but what happens with NMP? Now, I hope you do understand with anaerobic reactors, nothing happens with NMP. We will liberate NMP from the organic matter is coming into the anaerobic reactors. So ammonium will be generated from the proteins, and orthophosphate will be produced from the organic matter that contains the phosphorus. And often there is more ammonium phosphate in the effluent of an anaerobic reactor than orthophosphate and NH4 in the influent. So NMP will not be addressed in an anaerobic sewage treatment reactor. This means if you would like to address it, it has to be addressed in a post-treatment system. Alternatively, if you do consider the effluent for irrigation purposes, then NMP could be of interest for ferti-irrigation. And these are valuable nutrients and could be used for irrigation purposes. Now, let us go back in time a little bit to see how anaerobic treatment is implemented at full scale. Here you see an anaerobic reactor in India. In fact, the first anaerobic sewage treatment reactors were installed in Colombia in the end of the 80s, and then it was implemented in India as a part of the Ganga action program to clean up the Ganga. And this one is a 36,000 cubic meter USB in Kanpur in India. Now you can see these are very old data, and this comprises 4 years of monitoring. What is plotted here is a time zone of 5 years, and in the y-axis you see the BOD concentration. Now the BOD of this sewage was more or less something about 220, 230 milligrams per liter, and the influent is given by the squares at the top part, and the triangles down gives the effluent. Now what you see here that you have quite a irregular pattern of the BOD, but after a startup operation, a startup period, and do mind this is about half a year to 1 year, then the effluent gets stabilized and the reactor is operating with a stabilized effluent quality of BOD. Now the same holds for the total suspended solids concentration. We are treating raw sewage, so also the primary solids are, in fact, they are retained in the USB reactor. You see also a variety of influent data in the first part of the treatment in the first year. So the reactor was pretty unstable, but after 1 year, 1.5 years, there was much more stability. Now in the end, the suspended solids varied among 500 milligram per liter, and in the effluent it was a little bit less than 100 milligram per liter. So the chunk of the pollution is taken away by the anaerobic reactor. But you also see that the effluent values are relatively high. So you do need a post-treatment step. You do need an integrated approach of an anaerobic reactor and a post-treatment reactor to arrive to the legislative criteria. After these decades of development and decades of experience, we can more or less come to an efficiency for COD, BOD and suspended solids in full-scale application. Now this is a range of removal efficiency that you may expect in the implementation of municipal sewage treatment. Results are coming from Latin America, particularly from Latin America, with some results coming from India. Now that means the COD of the sewage is not very high, so it's not very concentrated. It's more or less 500, 600 milligram per liter. And the volumes of the reactor from very small, 100, to very large, to 50,000 cubic meter. Average COD removals, 65 to 75%, BOD removal between 70 and 80%, suspended solids removal between 65 and 75%, and pathogen removal very limited. In fact, maybe 1 log for coliforms, 1 to 2 log at the max, and helminth eggs also 1 log. So insufficient to have to serve as a complete treatment. You need an additional step. The full-scale experiences I will not touch that much in Brazil because we have other teachers from Brazil topping this topic. But to give you an overview, again, here is the treatment plant in Piracicaba, where you have an anaerobic reactor followed by an aerated lagoon. And interesting to see is the observed gas production, which was found in Brazil. My colleague, Professor Carlos Genicharo, he analyzed a number of plants in Brazil, and he divided the achievements with respect to methane production in the worst, in the typical, and the best scenario. If you do remember, theoretically, we produced 350 liters of methane per kilogram of COD converted. These are the data in liters per kilogram COD removed. And these data are lower. Since part of the COD is not converted to methane gas, but part of the COD is extracted from the anaerobic reactor as sludge, with the sludge removal. So that COD is also removed, but not converted into methane gas. The typical methane production observed in Brazil is something like 210 liters per kilogram COD removed, while the best scenarios reaches almost to 250 liters per kilogram COD removed. Once more, the rest of the COD is removed via the sludge. And in energy terms, the scenarios range between 25 megajoule per cube to 29 megajoule per cube. Right. To first address some design principles in designing an anaerobic reactor for sewage treatment. First, we have about the volumetric sizing. If you would like to dimension a reactor with a certain city, with a certain number of population equivalents, the first question is how big this reactor must be. Now, an anaerobic reactor of the type of upflow anaerobic sludge blanket, the USB reactors, we in fact design in 2 ways, based on the organic load and based on the hydraulic load. The organic load refers to the amount of COD that we can convert per cubic meter of reactor volume per day, and the hydraulic load is the amount of liquid that we can treat with the anaerobic reactor without washing out the sludge to the effluent. So, with the hydraulic assessment, the upflow velocity apparently is a very important criteria, and with the maximum, by determining the maximum organic loading capacity, the amount of active biomass that you have in the anaerobic reactor is an important criterion. First, dimensioning by the organic load. Well, calculating the volume is the concentration of the COD times the flow divided by applicable loading rate, an RV, a volumetric loading rate. Now, this volumetric loading rate depends much on the temperature. In this small table, you see the temperature from 15, 20, 25, and 30 degrees, and an applicable volumetric loading rate for sewage. Remember, sewage, about 50% of the COD consists of suspended solids, so the value of the applied loading rate is relatively low, much lower than for industrial wastewaters that are treating soluble influents. Well, in Brazil, most of the anaerobic sewage treatment reactors have a temperature of 20, maybe up to 25 degrees, so the RVs are in the range of 1.5 to 4. Now, if you extend that range from 15 to 30, then the RV is something between 1 and 6 kilograms of COD per cubic meter reactor volume per day. Then the next one is the hydraulic load. And this hydraulic load, calculating the hydraulic load, is the flow, the Q in cubic meter per day, times the hydraulic retention time. Now related to the hydraulic retention time is what I mentioned, is the upward velocity. We would like to retain all the suspended solids in our reactor by gravitational separation. Now a USB reactor is characterized by a secondary clarifier at the top. The surface load of the secondary clarifier is more or less in the range of the activated sludge secondary clarifier, not more than 1 meter per hour, and for sewage even a little bit less. And this upward velocity that can be simply calculated by the flow, cubic meter per hour, divided by the surface area of the anaerobic reactor. Now combining these two, we can calculate that the solids retention time is in fact equal to the height of the reactor divided by the upward velocity. Now the upward velocity, that has a certain value. As I mentioned, not more than 1 meter per hour. Now in the past decades, a lot of experience has been built up with full-scale reactors. And from their experience, the average upward velocity that is recommended is 0.7 meter per hour, which is more or less in a similar range as the clarifier of an activated sludge plant. And the design base in Brazil, most of these effluents are in the range of 20 to 20 degrees Celsius. Particularly in the states of Sao Paulo and Rio de Janeiro and Belo Horizonte in the state of Minas Gerais, the temperature of the sewage is more or less around this temperature, 22 degrees. And the reactor height for an anaerobic sewage treatment reactor is about 5 to 5.5 meters. Now combining this with the formula above, we can calculate that the average hydraulic retention time in the USB reactor is something like 7.5 hours. Now, if you now, with an unknown sewage, if you're now going to calculate the volume that we need based on either the hydraulic flow or the organic conversion capacity, we can make a diagram as I will show here. On the x-axis, the concentration of the sewage in kilogram COD per cubic meter of volume per reactor is given, and in the y-axis is the total volume the reactor is giving. Now assume that the flow is 250 cubic meter per hour, and the height of the reactor is, let's say, 6 meters. The volume of the reactor is the retention time times the Q, times the flow rate, in which the retention time is the height of the reactor divided by the upward velocity. Now the normal sewage range in the area of Latin America and Brazil is something between 300 milligram per liter, 800 milligram per liter, which is given here by the yellow bar. Normal sewage range for domestic sewage. Now then we can decide on the maximum upflow velocity. We can take a maximum upflow velocity of 1 meter per hour, or we can take the maximum upflow velocity, which is now the general common sense in Brazil, 0.7 meter per hour. Next, we can also calculate the volume of the reactor as a function of the concentration. In the first case, we calculated based on the volume of the reactor is based on the flow rate, in which the Q is fixed, the H is fixed, and the design upflow velocity is 0.7 or 1, so the volume is 1,500 or 2,200 more or less, linked to this upflow velocity. But now let's check if we include the organic conversion capacity, so the organic loading rate applied to the reactor. Again, the calculation is done by the concentration of the sewage times the flow divided by the admissible volumetric loading rate, the RV, in between 2 and 6 kilograms per cubic meter per day, 20-30 degrees Celsius. Now, if you start with a loading rate of 6, then the concentration, let's say we start with 2 at 2.5 kilograms COD, so we following that line. If we come to the normal COD range for domestic sewage, we see that this loading rate will be never met, never attained in a sewage treatment reactor, since the entire volume is completely determined by the maximum upflow velocity. The solid line in the yellow bar is far below the dotted lines of 1 meter per hour and 0.7 meter per hour. Meaning, very likely the anaerobic reactor will be underloading regarding conversion capacity, since it is limited by the hydraulic upflow. Now, the other loading rate is a 2 kilogram COD per cubic meter per day, and then the temperature is 20 degrees Celsius. Then you only see that with a very concentrated sewage of about 800 milligram per liter, the calculated volume by the organic conversion capacity is a little bit higher than the volumes of 0.7 and 1 meter per hour. However, soon, if the concentration goes to 500 milligram per liter, then also here the volumetric design, the volumetric sizing, is completely dependent on the upflow velocity and not on the organic loading capacity. And that is important to understand. So it is relatively easy to dimension an anaerobic sewage treatment reactor for the conditions that are prevailing in Latin America, like countries in Brazil. And you only have to deal with the hydraulic restrictions. Now, and that is then important to understand that for conventionally designed USB reactors for domestic sewage, municipal sewage, with the COD less than 1000 milligram per liter, they are generally hydraulically limited. The conditions are temperature higher than 20 degrees Celsius, COD of the influent less than 1000 milligram per liter, and the suspended solids in the influent less than 500 milligram per liter. Now, under these conditions, the volume of the reactor can be calculated with the retention time times the flow rate. And the retention time is the height divided by the upflow velocity, in which the height is something between 5 meters, 5.5 meters, maybe 6, and the upflow velocity not more than 0.7 meter per hour, maybe with a maximum of 1 meter per hour. Now, an example, this is Curitiba in Brazil. What you see here is a very huge reactor system for more than 1 million people. 24 modules, 2,000 cubic meter each. Total volume is 48,000 cubic meter of this USB. Influent flow 160,000 cubic meter per day. Upflow velocity 0.7 meter per hour. Reactor height 5 meter. And the HRT design is 7 hours. This is a conventionally designed USB reactors for these conditions. Now, interestingly, you can also see that the reactor is located in a relatively close vicinity of the urban area, so apparently there's no smell, and apparently the contractors they took all measures to combat smell and take care that no bad odors are reaching the urban areas. Interesting is also to see is the Archimedes screw influent pumps that brings the influent to a high level, and for the rest the entire plant is fed by gravitational distribution. So hardly any energy, fossil energy or whatever energy is used in operating this plant. Moreover, you generate quite a lot of methane gas. In constructing the USB reactors, it is in fact very simple. We feed a USB reactor normally from top to the bottom. And this wastewater is then in fact collected in a distribution box. From this distribution box, the wastewater is directed to the bottom, where the wastewater is distributed over the superficial area of the bottom of the USB reactor. Then we have a kind of a laminar upflow of the liquid at the upflow velocity of not more than 1 meter per hour, maybe 0.7 meter per hour. During the feeding, then we have an enormous reduction in velocity of the wastewater. So all the suspended solids, organic suspended solids, will settle, and we immediately have a CO2 removal efficiency of 50% of this anaerobic sewage treatment reactor. So when the temperature is 20-25 degrees Celsius and you start feeding with sewage, after a while the biogas will be produced by the sludge bed, and it will be collected by these gas collectors at the top part of the reactor. Now, the construction of these gas collectors create a secondary clarifier at the top part of the reactors. So this is called the settling zone. And the opening between the gas collectors is called the aperture, the area of the reactor where the velocity of the liquid is highest. Now then you will place some deflector beams to take care that all the biogas bubbles are indeed directed to the gas collectors and they do not enter the secondary clarification zone, because then they cause turbulence and, well, settling of the solids will not occur that adequately. And then you have to collect some effluent gutters and some gas extraction. Biogas will be collected, and the effluent will be constructed next to the gas collectors to discharge the effluent from the reactor system. Finally, you will extract the sludge, and you have some sludge withdrawal, and your reactor is ready. Now, do realize that the distribution of the effluent is above the liquid level of the reactors, which is causing a static head. And with this static head, if there is a clogging, you will build up some water pressure in the pipe, and by the increase of that water pressure, you have, in most cases, an automatic declogging of this clogging of the influent pipe. Now, all these criteria, they have numbers. They have design numbers. Think about the upflow velocity, as we mentioned, the height of the static head, the number, the density of the influent pipes, the angle of the gas collector, detention times in the settling zone, the concentration of the sludge bed, etc., etc. Now, all these design criteria, they will be discussed in detail by my colleagues from Brazil, which we will learn in another lectures of this series. Important is the primary treatment, the preliminary treatment of the influent before it enters the anaerobic reactors. I mentioned in the beginning that fine screens might be necessary, since we feed the reactor with these individual inlet tubes from top to bottom, and these, well, clogging should be prevented. The more debris is accumulating in the anaerobic reactor, the higher the chance that these influent pipes are getting clogged. So with the application of fine screens at the beginning of your sewage treatment line, we prevent this clogging, and the debris is taken out mechanically by an automated screen as shown in this example. Now, the screens here with these are automatically devices. That might be a very important but maybe expensive part of a sewage treatment plant, but it's very important to operate the USB without too many problems. And also sand should be removed. Note that the maximum surface load of grid removal should be 40 meters per hour and the scoring velocity of 0.3 meters per second. Well, we don't discuss that in this series, but this is preliminary treatment that is also needed for an anaerobic reactor treating sewage. And if not, then sand will accumulate in the anaerobic reactor and may cause to blockages and accumulation of a huge amount of sand inside the anaerobic sludge. Something we don't want. Take care about adequate influent distribution. As much as possible, we would like to work with gravity flow division, preventing a lot of pumping, which makes the system more vulnerable, but nonetheless, this hydraulic design in which each module is fed equally is very important. So high quality work is required here. In fact, each individual inlet pipe must receive the same amount of wastewater. Otherwise, we do not have this laminar flow inside the anaerobic reactor. Here you see some examples with circular or rectangular influent pipes, it doesn't matter. Quite some difference in numbers of pipe that are connected to one division box. Left is a reactor in Brazil. In the middle is a reactor in Bucaramanga in Colombia, which is maintained by an operator. Now this is in fact low skilled work. The operator is checking which of the influent pipes are clogged, and with a plunger connected to the stick, the person declogs this influent pipe every day. Now this can be circular or rectangular, that doesn't matter so much. Now just coming back, so why this is important? What we do want is an even influent distribution. So all the liquid is in fact in equal contact with the biomass. And the biomass converts the COD into methane gas. Now if some of these inlet pipes are clogged by debris or sand or whatsoever, then of course your influent distribution is disrupted. And in fact you may bypass part of the reactors, and raw influent may rapidly go upwards to the effluent of the reactor. You see a deterioration of your effluent efficiency occurring when this influent distribution is not well designed. The anaerobic sewage treatment that was developed in Latin America, that was in the 80s, 90s, later on in the 90s, early 90s, it was transported to India, and then there was a huge development in each of these countries, and at the moment there are thousands of reactors are in operation. There's yet limited operation in countries like Sub-Saharan Africa. There are some of these reactors were trialed, and in principle they showed interesting results, but there are also some constraints that I would like to discuss. We were involved in the construction of this anaerobic sewage treatment reactor in Accra, Ghana. It was a 6,500 cubic meter USB reactor for the municipal sewage treatment at the center of Ghana. The reactor is located just next to Kola Lagoon, and the reason they went for an anaerobic reactor were multifold. One, there was no space for a pond system, in which most of the Sub-Saharan Africa countries have most experience. But there was simply no space. And they didn't want to go for activated sludge because of the energy concerns. And also about the sludge concerns of the growth of the sludge. But the energy concerns were most important then. So they came to the conclusion, we have to go for an anaerobic treatment, and let's combine it with a very efficient post-treatment like in a high-rate trickling filter. Now here you see the construction of this anaerobic reactor, and in the just below Kola Lagoon you see the high-rate trickling filters. Now at the end of the 90s, early 2000s, the reactor was finished and it was started up under the auspices of the Accra Municipality Agency, together with the British firm Taylor Woodrow, who constructed the plant. What you see here is the USB reactor, and the entire construction was elevated. And the reason for this is that the groundwater table here is very high, and sometimes in the rainy seasons they have a flooding of that area. So they decided we have to raise the reactors above ground, which is a relatively expensive exercise. Do remember the examples that I showed you in Latin America and India, where most of them they were excavated, so a large part of the height of the reactor was below surface level. Now in the middle you see two red bars, and that indicates the support for the fine screening and the sand removal, the grit removal, before the influent is distributed to the 6 reactor modules of each, a little bit more than 1,000 cubic meter. Now up front here you see the sludge drying bays where the accumulating sludge is dried, and on the left you see 2 circular high-rate trickling filters. Now to go to the results of this reactor, you see some peculiar observations. In this table, you see the COD, the BOD, the TSS, and the VSS concentrations of the influent. You will also see next to that column influent peak values, with COD values 10 times higher, and TSS values as well, more than 10 times higher. Then you see the effluent of the USB reactor, the effluent of the trickling filter, and the effluent of the clarifier. In fact, the reactor amazingly worked super. Very good. But there also comes some constraints here. One constraint was that every Friday we observed that the pH went to 5 to 12. And the problem was that there was a soft drink factory very close to the inlet of our reactor, and every Friday they were cleaning the tanks with soda. And it was simply dumped into sewer, and we faced every Friday a problem. And then there was another observation we made. The COD efficiency under normal operation was over 92%. The BOD TSS efficiency, 98%, was very well. However, you also see these peak values, huge peak values, 10 times more COD than anticipated, and the same for the sludge. Now, what was the situation here? The anaerobic sewage treatment plant only served a very small area of the city, maybe 10% or less than 10% of the municipality of Accra. The rest of Accra was equipped with on-site sanitation, septic tanks, but also night soil containers, and these were desludged by the tanker trucks. And what happened at the tanker trucks, they dumped these solids into the sewage system, and the sewage system was pumped to the anaerobic reactor. Now that can also be seen is that the ratio of the normal sewer is COD-BOD is 1,600 divided by 1,000, but from the influent peak values it was 16,000 divided by 3,000. So apparently this is septic tank container content dumped into the sewer. Now this amount of solids, this was not anticipated in the design of the reactor. The reactor was designed from an HRT of 8 hours only, but we had to increase the HRT, so to reduce the flow, getting an HRT of only 1 day, despite the temperature of 30 degrees Celsius. Attributable to the peak values of sludge that was dumped into the sewer and conveyed to the anaerobic reactor. Nonetheless, during the trials, the reactor operated quite well. Here you see the USB reactor in function, the trickling filters, and the final clarifiers with reasonably clean wastewater, treated wastewater. Now, looking to the average concentration, on the y-axis the COD is given, BOD, COD and TSS concentrations, and on the x-axis is the course through the anaerobic aerobic reactor system, the influent, USB effluent, trickling filter effluent, and the final effluent. Now you immediately can see that the chunk of the solids and the COD is dealt with in the anaerobic reactor, and the rest is taken away in the trickling filter part. Now this plant operated well for about 1.5 years, I believe 2 years. But after this plant was handed over, problems with the plant occurred. There were too little spare parts, and in fact the entire operation of the plant collapsed. To my point of view, this is kind of a white elephant in the handover of the technology was not well embedded in the project that was executed. Now, some examples of a decentralized sewage treatment plant. Since we do not need mechanical aeration, we can size a treatment plant from very large, what you saw 50,000 cubic meter volume, to very small. And that means we can use them in a decentralized setup. For instance, in areas that are distant from sewer systems. Now here you see two examples, one in Campina Grande that was tried in the, also in the 90s, and another one in the right you see in Maipe, Brazil, 6,500 in the population equivalent, which is a USB reactor and a submerged filters. Do note that in a country like in Brazil, in the city of Recife, it was a policy was adopted to go for decentralized approaches rather than to the construction of trunk sewers with large pumping systems to carry the wastewater from one part of the city to another part of the city. Now, instead of pumping stations, decentralized treatments were proposed, among which drinking filters, but also among which several USB reactors were installed. However, in the left side, this example in Campina Grande was also collapsed. It was constructed, and indeed that area was served with this treatment plant, but maintenance must be guaranteed. And in this case, the maintenance was not well guaranteed. So it was constructed, but after a while also this plant collapsed by malfunctioning because of lack of maintenance. And in the right, this reactor is still running since it is supervised adequately by a sewage company. Another example is in Sanhour, Egypt, the northern part of Egypt, so the Mediterranean coast until Upper Egypt, the south part. It has very high temperature, and also here the concentration of sewage is quite high, because drinking water distribution is limited. There's not a large amount per capita, but drinking water, so concentrations are high, and also small factories discharge their sewer in the centralized sewer systems. Now, in this case, an analysis was done on the different types of wastewater treatment systems. They convert activated sludge with lagoons and with a USB, with a trickling filter, and they came with this solution: an upflow anaerobic sludge blanket reactors, followed by the stone trickling filter, which was already there as the main treatment. So, making an anaerobic treatment preceding the trickling filter that was already installed there. And comparative analysis showed that the investment costs were 40% lower applying the USB reactor, and the operation and maintenance cost was 85 to 90% lower, mainly attributable to the fact that no energy requirement was there operating the USB and trickling filter. Now, then we have another example of decentralized treatment in a rich area. What you see here is an urbanized zone in the city of Mérida in Mexico. You see a trickling filter, and also this trickling filter is preceded with an upflow anaerobic sludge blanket reactor. Interesting to see here is how this trickling filter is constructed. It is filled with ornamental stones, so they have a very large open surface area in which the biofilm can grow. It's very well distributed, the anaerobic effluent, over this trickling filter. And moreover, it is located inside this urbanized zone in which relatively rich people live. But Mérida, Mexico, is relatively dry. So instead of pumping the effluent to the main sewer line, they said we would like the effluent of this sewer plant to use for irrigation, greening the city areas. Now, they made some construction that there is no smell, and they succeeded in that. And they can now use the effluent, dechlorinated effluent, for greening the city areas. If a USB reactor technology is still too complicated, alternative anaerobic processes can be used in conjunction with a post-treatment system. One of the oldest is the known septic tank system, already over 130, 40 years old, developed by Donald Cameron. Now, this system was in fact developed to scavenge the solids from households or from communities in a kind of a tank, in an anaerobic tank, in which the solids are settled to the bottom. Floating sludge is floated to the top in a kind of a scum layer, and the effluent, after the baffled, is then discharged to an infiltration zone, which you can do in a low density area. If the density increases, you can connect the effluent tubes to a small bore sewer system for discharge elsewhere, or to equip an additional post-treatment system to the small bore sewer system. Now, this strategy is equipped either for isolated houses, for communities, or for even urbanized area. One problem of a septic tank, and then I go back one more to this slide, is that the incoming influent is in fact bypassing the anaerobic sludge. The sludge is only consisting of solids that are settling, but the growing methanogenic bacteria, they are not in contact with the soluble BUD, which is coming in with the influent. So this is not meant as a treatment step. No, a septic tank is developed as a possibility to retain the solids and to have a solids-free effluent to be infiltrated in the soil. But nonetheless, this design of a septic tank is still copied as a part of a treatment system. Much more clever is to come with an upflow septic tank, because in this case you force that the incoming influent is mixed with the anaerobic biomass, including the methanogens. And what you then can achieve is an accumulation system for the solids. They will be entrapped in the sludge bed, but also is that the soluble COD, BOD, is converted by the anaerobic organisms to methane, meaning it is not treating the solids only, but also the soluble COD. And you have a much more improved contact between the soluble C and the biomass. Now, this system was developed in the early 90s, and it was further and further advanced. And our colleagues from the Asian Institute of Technology in Bangkok, they even coupled it to a solar panel in which they heated the effluent of this upflow septic tank to 50 degrees for enhanced sterilization of the treated effluent. Now with these, if you treat black water with this, you can reach up to 90% removal efficiency. And with gray waters, maybe even also 80% removal efficiency. So quite interesting low-cost systems, anaerobic systems, that can be coupled to a proper treatment technology. Now for more larger flows, still an IMOF tank could be of interest, but of course nowadays you cannot emit methane gas anymore to the atmosphere, and care should be taken that the produced methane is collected and at least treated with a compost filter to prevent methane emissions to the atmosphere. Post-treatments can be consisting of conventional trickling filters or high-rate trickling filters or other type of treatment systems. One of the systems that is currently more and more applied is the anaerobic baffled reactor. In fact, the anaerobic baffled reactor is a sequence of anaerobic upflow reactors. Now, since there are no tubes, individual inlet tubes, but this is a mass flow, there is low clogging risks. No complex influent distribution, only baffles, high active biomass concentration, and low surface demand, about 1 to 1.5 square meter per cubic meter of influent. You need to monitor the sludge level, and you should be careful with high hydraulic flows, because with high hydraulic flows you may carry over your sludge to the last compartment and finally to the effluent. So in fact the upflow velocities in each of these baffles is more or less equal to the upflow velocity in a USB reactor. So in principle this reactor is larger than a USB reactor. Nonetheless, some design and operational features of this anaerobic baffled reactors. Minimum retention time is 2 to 3 days. Remember, a USB reactor is designed for 8 hours. But this with 2 to 3 days with low maintenance will give you 80 to 90% COD removal. Similar to your USB, 8 hours per segment retention time and 2 hours in a settler. The minimum solids retention time is 100 days. That means the solids are well digested and can be discharged and dried in sludge drying beds. The optimal temperature of the system, 25 to 30 degrees Celsius, pH 6 to 8, CN ratio 50 to 30. It's a continuous flow-like system, and it can accept hydraulic and organic shocks. But don't press the system to too high shocks. Then a bigger system needs to be designed. Upward velocity inside the segments about 0.7 to 1 meter per hour, just like a USB reactor. And the organic loading rate maximally is 3 kilograms of COD per cubic meter per day. The biogas production is something like 15 to 27 liters per person per day. But nonetheless, this system can be constructed without the use of any energy sources. So it is a very plain system for communities that are poorly served. If you then go one step further and go to very high density communities in low income countries, anaerobic conversion can also be used to directly stabilize fecal matter and urine. Now, this is an example where the toilet systems are connected to a digester, a biogas digester, in a contained environment. And that's very important to prevent diseases, to prevent water pollution, protect drinking water sources, produce nutrients, produce soil condition, produce energy. Now the energy is not that much, and we have to be realistic. The COD of the fecal matter is 38 grams per person per day, and the COD of the urine is something like 9 grams per person per day. This is an example where this is applied. This is from Kampala and this is Kenya, Nairobi, Kibera slums, where a block sanitation is applied. People that pay for making getting use of the toilet systems, so they pay something like 10 shilling, and a caretaker takes care of the cleanliness of the installation. Then we have female and male toilet systems, but we also have showers there. And the showers, they can be heated with the energy that the system is producing. Now, at the side of Kenya, it can be quite cold in some times of the years. So a shower system is a kind of a surface of the toilet block. Now, then the energy, energy is a problem in such areas. These mother and the young daughter, they are carrying wood to the area. But in fact, the fecal matter, you can convert into bioenergy. And you can calculate that maximally you may produce 150 watt hours per person per day on energy. And that energy can be used for cooking. Of course, you have to make it appealing and not directly connect the kitchen to the toilet block, because nobody would like to cook near a toilet block. So you have to make a design that is acceptable for the local users where the kitchen is placed. But in principle, the biogas that you can produce from the fecal matter can be used as an alternative energy source for cooking. Now, some of these toilet blocks there are built. What I mentioned in Nairobi is one, Kisumu, but also in Kampala, Uganda, these toilet blocks are built. Now, these toilet blocks are multifunctional, and they are built in this way. So below you see the digester. In the ground floor you have the toilets and the showers. The first floor here you have some meeting rooms, offices, kitchen and resource centers. The top floor is some open sites, simple roof for large group meetings. Design, HOT 120 days, 300 to 600 population equivalent per day. And you have also connected to this possibilities for water vending. Down to earth, low cost sanitation solution, non-sewage, where you have a direct collection of the fecal matter and conversion of the fecal matter of the urine in stabilized sludge in an energy carrier, methane gas. Now, concluding this lecture, anaerobic pretreatment of municipal sewage offers cost-effective and compact solutions for BOD removal, COD removal, with efficiencies for BOD 75 to 80%. Note, N and P are not addressed. This is about suspended solids and organic matter removal. USB technology for sewage treatment is well accepted in Latin America, with Brazil as front runner. India is a good runner-up. This adequate treatment performance is required, well-designed, and a well-constructed reactor system, and also take care of well-trained personnel. It's a reactor, and a reactor needs to be maintained. It's not the magic box, so you need people with some knowledge that understand what's going on in the tank. Then co-treatment of fecal matter with municipal sewage in USB reactors is possible, but to a limited amount. An HRT should not be extended. If a lot of septic tank solids are entering the USB reactor, the USB may lead to failure, and you need to adapt your hydraulic retention time to longer periods. And finally, fecal sludge can be stabilized in on-site and off-site anaerobic digesters with biogas for energy recovery as an interesting option. I hope that these examples gave you some ideas about how and when anaerobic treatment can be used. Now, the rest is mainly about the municipal sewage treatment with anaerobic reactors. And I do wish you a lot of interest in learning what is possible with anaerobic sewage treatment to take the best advantages of the state-of-the-art of the technology that is currently offered. Wishing you all good luck in the remainder of the course.